Welcome back, dear students. So, we will be continuing with the process concept. In this video, we will be covering process scheduling, where we'll be discussing about process scheduling queues, including ready queue and various other IO device queues. Along with this, we'll be also discussing about the representation of process scheduling. So let's begin with the process scheduling. Basically, we want optimum efficiency from our system, uh, for which we need to get maximum CPU utilization. For this, multi-programming basically aims to have some process be running with the CPU at all times. Like in time sharing system, it aims to switch CPU cores among processes quite frequently so that users can interact with each program while it is running. Have you ever thought of how it is possible while you are working on your machine, you are able to listen to some songs and at the same time you are browsing internet. Along with this, you are also downloading a movie from internet and also you are copying something from your pen drive onto your machine or vice versa. So how all these things are going on simultaneously? So, if your machine is able to do so, it means that your machine is supporting multi-programming. Multi-programming aims to have some processes running at all times to maximize CPU's utilization. Multiple programs can run concurrently on your machine only if the processor which is there in your machine is having multiple cores or your machine is having multi processors. In case your machine is having a single processor with a single core, in that scenario, only one process will run at one time. It is the scheduler which selects a process from the processes available in the main memory and passes it on to the CPU core for its execution. One core can run only one process at one time. In case the number of processes available in the main memory are more than the number of free cores available, in that case, some processes will have to wait until the CPU core is free to begin the execution of that process. The number of processes currently running in the memory is known as degree of multiprogramming. Fine. I hope you got the point. So let's see. Uh, let's have a look on process scheduling queues. So basically, OS maintains scheduling queues of processes. The job queue contains the set of all the processes that are in the system. The ready queue contains the set of all the processes that are residing in the main memory. These processes are waiting for the execution. The moment the CPU is allocated to them, the execution of the process begins and the process moves from ready state onto running state. Running state means the allocation of CPU is done to that process. During the execution of the process by the CPU, if the process needs to perform some IO activity, then that process is shifted to device queue. Upon completion of the IO activity, the process again comes to the ready queue where it waits for the CPU to be allocated. In case the process completes its execution, in that scenario the process comes to an end. So if you see in the figure below, the jobs, as far as the job queue is concerned, as I've told you, it contains the set of all the processes which are there in the system. So the processes are transferred or migrated from job queue onto the ready queue, where multiple number of processes are waiting for their turn in this ready queue so that they can gain the access of CPU. The moment a process gains the access of CPU, it basically executes over there. And let's suppose that the process which was executing, it needs to perform some IO activity or some IO related event is supposed to happen so that this process can continue with its execution. So in that scenario, the process is switched from the CPU's execution onto the waiting queue of IO devices, where once that IO activity which was supposed to be done on this process, once it is completed, then this process again moves into the ready queue and is waiting for its turn for the execution. The moment this process gets the CPU for its execution, so the process execution takes place, and let's suppose this time this process has done its entire job. In that case, this process will come to an end, or we would say the process terminates. So now let's have a look over here. If you observe in this figure, we can see number of queues like ready queue and various device queues for first of all I have told you about ready queue, then various device queues like magnetic tape, disk and terminal. So are shown in this figure. In fact, if you see over here, there are two queues for which are representing magnetic tapes, that is unit 0 and unit 1 for magnetic tape. So this means that we are having two instances of the same device, in this case that is magnetic tape. So these multiple instances of same device can be allocated to two processes simultaneously. For example, if a process P1 is looking for magnetic tape and at the same time process P2 is also looking for magnetic tape, in that case both these processes can be allocated one copy of this tape to one copy of this tape can be given on to process P1, and second copy can be given on to process P2 so that they can do their jobs. So if you observe over here, as far as ready queue is concerned, the header part of the ready queue, in fact, for all the queues over here, the header part contains two components. One is head and second one is tail. So in the ready queue, as of now, we are having two PCBs. PCB is process control block, PCB number 7. Suppose it is representing process 7, and this is the PCB number 2. Suppose it is representing process 2. So a ready queue header, if you see over here, the queue header of ready queue, it contains a pointer to the first PCB in the list, that is PCB 7, and each PCB header includes a pointer field that points to the next PCB in the list. When a process is allocated CPU core, it executes for some point of time and eventually it terminates, or it is interrupted, or it waits for the occurrence of particular event such as completion of IO request. So basically what I'm trying to say over here is whenever a process comes for execution and it is with the CPU, so during that time, during that phase, there are three possibilities over there. Either that process will terminate, I mean to say that process has done its job and that process will terminate, or that process is interrupted, maybe because a higher priority process has come in the system which needs to be given CPU's time immediately. In that case, this process which was executing as of now has to leave the control of CPU in between and is transferred from the running state with CPU onto the ready state. The third possibility is that when this process was executing, actually it needed some IO activity to be done, or it was or some occurrence of particular event was supposed to be done. In that case, this process has to wait. So once that event takes place, then only this process is brought back again to the ready queue. So let's suppose that the process has put an IO request. Actually, the process, let's suppose process P7 was executing. Fine. And this process P7 was with the CPU during its execution process, during its execution phase. And this process has put an IO request to a device. Let's suppose disk. I mean to say, this process was executing. In between, it has requested some IO. It has put some IO request for a device. Let's say disk. Now, question is that what will happen when this will put an IO request? So this process is switched from the CPU onto the waiting queue. Fine. So once it is in the waiting queue, it is looking for the disk. If the disk is available, if the disk is free, then this process, that is P7, will get the access of the disk. Fine. So it will do whatever task it was supposed to do with the help of the disk. That task is done. Now this process is again brought back into the ready queue. And now this time it is at the end of the ready queue, I would say, because suppose earlier there were some processes in this scenario. If we see PCB2 was already over there. Fine. So first of all, before explaining this part, what happens when P process 7 was shifted from the running state, that is from CPU onto waiting queue? Will the CPU sit idle in this scenario, because the process which was executing is shifted from its control, that is CPU's control, onto waiting queue? The CPU won't sit idle. In fact, the next process which was there in the ready queue is given the access to CPU. So in this system, if you observe over here, as PCB7 means P7 was executing, the next process which was waiting in the queue was PCB2 or process 2. So process 2 will gain the control of the CPU this time. In the meantime, what was happening over here, this process was requiring some disk related activity. That activity was done. Now once that activity is complete, this process is shifted back onto the ready queue, but at the end. At the end means, because if some other processes are already waiting over there, let's suppose in the meantime P6 was also over there, then P3 was also over there. So P6 would be in the beginning. Let's suppose it is waiting for its turn. So its header will be pointing on to P3, because P3 is the next process, and P3's header will point to, let's suppose now P2 enters over here, so it will point to P2. Fine. So in that way, P2 is the last process to enter in the ready queue. So first P6 will get its turn in case the things are going on in order. Then P3 will get the access to CPU, and then P2 will get the access to CPU. So I hope you got what I'm trying to say. So a new process is initially placed in the ready queue, and it waits for its turn for execution. As I've told you, P2 and P3 were the new processes. The moment they comes into system, they are first of all brought into the ready queue, and thereafter they wait over there for their execution. So let's move on to the next part. So if you see over here, in this figure, we are showing you the representation of a process scheduling. So once a process is allocated a CPU core and that process is executing, there are several events which can occur now. In fact, there are 4 possibilities over here. The first possibility is that first of all, what happens, the process was in the ready queue. Let's suppose P1 was in the ready queue, and thereafter P2 was there and P3 was there. So as of now, the ordering is first P1, then P2, and then P3. So what happens over here is, the moment the CPU is free, this P1 gets the access to the CPU. Now, there are four possibilities that can take place with regard to this process. The first possibility is that this process needs some IO activity to be done first, so that it can complete its remaining execution. In that case, this process will be put onto the IO waiting queue. Why in IO waiting queue? Because suppose that it is demanding for, let's suppose, a tape, a device named tape, to complete its IO activity, and that tape is not freely available as of now. So this process is waiting for the availability of the tape. The moment the tape is available, this process P1 is put onto the access, is basically allowed to access the tape now. So it is working on with the tape to do its remaining activity. Fine. Let's suppose, in fact, I would say, if there are more number of devices already, more number of processes already waiting for tape, let's suppose the moment P1 came for the access to, was demanding for the access to tape, already P7, P9 and P3 were, suppose P10 were already there waiting for tape. So this will be waiting over here for the access to tape. So P1 is also waiting. So it is in the IO queue for tape. The moment P1 gets the access to tape, it will do its job, and once the job is done, it again enters onto the ready queue at last. Fine. So uh, this is again waiting in the ready queue to get the access of CPU. So again, when its turn comes, it can do its remaining job. So that this is the first possibility with regard to the process. The second possibility is that, so suppose that we are working in a time shared system where we have set a quantum or a slice, we have discussed this term earlier also, or a slice of certain milliseconds. Let's suppose 5 milliseconds. 5 milliseconds. So each process will get CPU for 5 milliseconds in one go and can do its job. So actually process P1 was executing, and during its execution these 5 milliseconds have elapsed now. But the task which was supposed to be done by process P1 is not yet complete. Still, it has to leave the control of the CPU because the time slice has expired. In this case, it straightaway moves back at the end of the ready queue, and it again waits over here for some time so that it can gain the access of CPU and can do its remaining job. The This was the second possibility. The third possibility is that when that process was executing, suppose the process P1 was executing, so during its execution it has created a new child. That means P1 is now a parent and has gone for creation of a child. Let's suppose that name this process as P1.1. Just to have an idea that 1.1 is a child of a process P1. So in case a new child process comes into picture, in that case process P1 itself will not continue with its execution till the time process P1.1 completes its execution. So P1 straightaway moves on to the waiting queue, and it stays over there in the waiting queue till the time P1.1 completes its execution. So once P1.1 completes its execution and is terminated, then P1, which was waiting in the this waiting queue, is shifted on to the ready queue, where it waits for the allocation of CPU. It is now basically in this queue where it waits for its turn for CPU, and this time, if in case it completes its job, it can move on to the termination state. The last thing is, another possibility over here is P1 was executing, but what happens over here, some other process comes into the system which is having some higher priority as compared to P1. In that case, this P1 is interrupted, and Due to this interrupt, this P1 is required to leave the control of CPU so that the higher priority process can take the control of CPU now. So in that case also P1 shifts from or migrates from the CPU's running state onto the waiting queue, and it again waits over there till the time it turn comes and it can complete its remaining execution. So in first state as well as in the third state, or in these two cases, the process eventually switches from the waiting state onto the ready state and then is put back into the ready queue. Ready state and ready queue, I'm using two terms over here. Ready queue means where different processes are already waiting. There may be a scenario that there no process is waiting in the ready queue. So this the one which is coming will be the first one to enter in the ready state and will immediately get the access of CPU whenever the CPU is free. So a process continues this cycle, that is from this stage on to ready queue, then again to CPU, then again to this. It keeps on continuing this cycle until it terminates. At this time when the process terminates, so in that scenario it is removed from all the queues and also its PCB, that is the process control block which was residing in the memory, and whatever resources were allocated to this process, they all are deallocated now, because during its execution process needs number of resources and it acquires those resources with the help of which it can complete its job. But once the job is completed, then the PCB, that is the process control block, as well as all the resources which are allocated to the process for its execution, they all are now deallocated. So that's it from my side with regard to the process scheduling. I hope that you have got the idea that what process scheduling is. So uh, in the next topic, we'll be going for discussing about the various operations which are feasible on the processes. And that's all. Thank you.